All right, so let's give a brief introduction to projectile motion, the equation we'll use, and we'll see how we use them in an example. All right, so we already know what a projectile motion is a motion in two dimensions. It's a motion in 2D. And in general, the only rule that is applicable is that the x component of the acceleration is 0 and the y component is not 0. All right, this is the only definition, okay, which means it has only vertical acceleration. A typical example is the two-dimensional motion of objects under the influence of gravity near the surface of the Earth, right? So if it's a 2D motion, we have to use component method with all vectors that we're going to deal with. All right, so remember what are the vectors, right? Is acceleration, displacement, initial velocity, final velocity, right? And of course, we have time, which is not a vector. Okay, so how do we visualize the projectile motion? Well, here's a plane. All right, this is up, and this is, I don't know, east, west, whatever it is, to the right. So let's say that we have a projectile, all right, and we're throwing this projectile from some initial height at t equal to 0. We're throwing it with some initial velocity, vi, right, with some initial angle, theta I. So for example, you can throw a basketball at 45 degrees or at 50 degrees, whatever that is. As a result, what will happen is, since there is gravity, the object will go through a trajectory, let's say somewhere here, and we'll get there, right? So our object will go through different stages. Eventually we'll get here, here, and eventually at the final point, right? So again, this is our initial velocity. We measure the angle with respect to the horizontal always. So this is my initial point, and this is my final point. So there is going to be a displacement, right? And the displacement is, as we know, the shortest path from initial toward final. So this is delta d, okay? And our object will have some final velocity that will look, so I'm trying to find, will look something like this, right? V final, okay? And of course we have the acceleration. And remember that the acceleration is only downward under the influence of gravity is 9.8 meters per second squared pointing down, of course, here on Earth, right? So what we're going to do now, we're going to split all the vectors that are here into components, x and y component. Remember, this is y, this is x. All right, horizontal and vertical components. So let's start with velocity. Initial velocity is going to have the x and the y components, and I'm hoping we remember how to find them. Vf, let's use red here. That's why we did all the review of components of vector math, vfx and vfy, right? And the same with displacement. Displacement has delta dx, which we call it range, the horizontal displacement, and delta dy. All right, so there you go. That's what we do. And now we study all the horizontal. So what we're going to do is we study horizontal component and vertical components separately. All right. The only thing that is common is time. It's independent pretty much. It doesn't matter what happened, all right? So what's going on is, from horizontal point of view, as you may have seen it on the basketball video analysis, horizontally, a projectile moves in uniform motion. Why are we saying that? Because AX is 0, right? Vertically, a projectile moves in uniform accelerated motion, right? AY is actually gravity. All right? And that's what we do. We use our knowledge of uniform accelerated motion and our knowledge of uniform motion to study a projectile motion. All right? So let's start writing now X and Y separately and see what equations we are going to use and what variables we're dealing with. So let's start with horizontally. Vix is Vi cos theta I, right? Is the X component. Viy is Vi sine theta I. Remember, plus or minus, depending what you choose as positive, up or down. Ax obviously is 0, the very definition of projectile motion. Ay for free falling motion is g, right? Whatever g is. What else we have? Now we have Vfx, the x component of velocity, never changes, right? So it's equal to Vix. Remember, is constant. I'm going to write here, this is uniform motion. This is a free falling motion. All right. Now we start writing the equations. Vfy is equal to Viy plus acceleration times time, right? Delta dx, the range or the horizontal component of the displacement, is Vix times delta t. Why am I writing that? Because it is a uniform motion. All right. In here, we can use any of the uniform accelerated motion equations. So I'm going to write all of them. Delta d and delta d and Vf equal to Vi delta t plus half of acceleration delta t squared, Vf delta t minus half of acceleration delta t squared, Vi plus Vf divided by 2 times delta t, and the last one I have to erase, then go further down. Vf squared is equal to Vi squared plus 2 times the acceleration times delta d. The only thing that I'm going to add to all these equations is the y subscript, because we're talking about the y component only of the projectile motion. So all the vectors are having the y, denoting and making sure that we're all aware that we're talking about the vertical y component only. All right. And remember, time is common or independent. And that's how we're going to solve the projectile motion problems using this knowledge. By the way, a lot of misconceptions happen about this top or up point. If I were to ask you, oh, what's the velocity there? And I'm going to pause here. A lot of you, or most of you, or some of you are thinking, oh, it's zero. Remember, it's not zero. In here, it has only x component, right? Only Vy is zero at the top, right? The projectile does have velocity there, but only the x component. Okay, so now, once we have this knowledge, we're going to be able to solve projectile motion problems.